Let's give people tests. Okay. Let's give people a couple more minutes to settle it down. Okay. So it's my pleasure to introduce it's my pleasure to introduce Shuai Yan. Shuai did his undergrad at the University of Science and Technology of China, like many great geophysicists, and came and did a PhD with us at the University of Texas, where he worked on one of the largest previously undiscovered subglacial lakes in Antarctica, then at the time called Lake Snow Eagle. Since then, he's gone on to do a postdoc at the University of Washington, where he's working with the glaciology group there, and has been an integral part of the Center for Oldest Ice Exploration. So with that, go ahead.
Test, is audio working? Awesome. Yeah, thanks, Duncan, for the introduction. Yeah, we got a different room today. It's quite nice. I walked past the UTIG seminar room this morning. I was like, why is people talking in there? But it's nice. Yeah, so happy to be here. Happy to show some of our recent work. The title for this talk is Probing Antarctic's Deepest Secret. I know it's kind of a cheesy title, but I chose this title because I remember when I was a graduate student at Jackson School, one of the first classes I took was called Earth in Deep Time. Back then, I find the phrase deep time really interesting. I never worked with that expression. You know, deep typically is used to describe spatial dimensions. So I find that phrase quite interesting. But it makes sense, right? If you look at geology record, older history is typically deeper. Of course, over the years, that phrase became more and more natural to me. I don't really think about it more. Fast forward onto about a few weeks ago when I started thinking about this presentation, I was trying to find a thread to connect everything together, or a central theme, and the word deep came to mind. Because I realized for my PhD work here and for my postdoc work at the University of Washington, I'm essentially working on one of two things, either the deep structure of the Antarctic ice sheet or the deep time evolution of the Antarctic ice sheet. So I want to design this talk around those two themes. Uh-oh. There we go. Okay. It's working. Nice. So yeah, like Duncan mentioned, my current position at UW is funded by COLDEX, which stands for Center for Oldest Ice Exploration. It's the NSF Science and Technology Center. And all the work I'm presenting today truly represent a team effort. So I want to acknowledge COLDEX and all the participating institutes within COLDEX before I start introducing the work. So the research effort within COLDEX can essentially be roughly divided into four different categories. There is exploration, and that's, I believe, where most of the UTIG contribution goes into. And there is ice sheet modeling. That's where my current work mostly goes into. And there is ice coring and analysis, so that we have people actually go to the field, drill the core, bring them back, and do geochemistry experiment on them. And we do have some technological intervention effort going on as well. So the overarching goal of COLDEX is to find old ice cores to support better reconstruction of paleoclimate evolution, right? And so this figure shows some of the data points we had before COLDEX. This blue curve, I really want to highlight it. This blue curve in the top panel is one of the oldest continuous ice core we had. It's the Epicodome C ice core. It was drilled 20-something years ago. It's about 800,000 years old, so it gave us a continuous record of paleoclimate evolution for the past 800,000 years, which is quite amazing. Beyond that, we have many data points that are not continuous, but much older. So we call them snapshot cores. So instead of a continuous movie, they gave us a snapshot of the Earth's climate condition at a certain point of time in the past. So the goal for COLDEX is essentially twofold. One, we want to find an older continuous core to extend this continuous record, hopefully into the 1 million years old range. And beyond that, we're hoping to find some non-continuous snapshot cores that's much older. So that's the overall goal. COLDEX has been exploring 2 different sectors of Antarctica to achieve this goal. For the continuous core, we have been working on what we call the interior side, essentially the southern flank of Dome A. And for the non-continuous core, we have been working on an area of Antarctica called Allen Hills. It's on the edge of the ice sheet, not too far away from McMurdo Station, where old ice is being preserved at a very shallow depth. So the majority of my work is actually on the interior side, and that will be the majority of my talk today. And if I have time by the end, I'll give a quick shout out to the Allen Hills team. Okay, interior side, is what we call it southern flank of Dome A. In some paper, you may hear the phrase Dome A South Pole Corridor. Essentially, it is this part of East Antarctica. You can see the surface contour on this map, higher elevation here, so you can imagine the ice flow going kind of this direction, right? Following the contour. And we do have some pre-existing data before COLDEX. You can see this is the data coverage map from Maps 3. There is some data, right? Not very dense, but we do have some pre-existing data. And based on those data, we can get a sense of the basal topography of this region. Right? We can see the Gambersiv mountain beneath Dome A, which is known for its very rough topography, right? You can see all the ridges and valleys. We know there is probably a basin next to South Pole, and there are probably a few mountains within that basin. So we know something about this part, but nevertheless, you can see it is still one of the biggest data gap in terms of our geophysical data coverage. So COLDEX went in, did 2 seasons of airborne geophysical survey. It's a very well-designed survey. You can see the majority of the survey transect, they're aligned with the ice flow direction, which I personally very appreciate. It makes modeling effort much easier. There are some cross-flow transects as well. We can use them to do things like leveling the potential field dataset. We can use them to do cross-transect comparisons, things like that. So this is a survey aircraft. It's BT-67. We put skis on it so that it can take off and land on the surface of the ice. You can see the UTIG radar antenna beneath the wings, and we have another radar system provided by the University of Kansas on the same aircraft. So we have 2 independent radar systems installed on the same aircraft, which is kind of a technology breakthrough. You can see the magnetometer sticking out of the tail of the aircraft, and inside the aircraft, we also have a gravimeter measuring the gravity field. I took this photo the other day at the LEGO store. Apparently, they came out with a set for DC-3, which is essentially the same airframe as we use for the survey BT-67 with different engine and stuff, but essentially it's the same aircraft. And it was so popular during the last century, very popular in the commercial world, very popular in military application as well, and now it's still in service in polar expedition. So that's pretty cool. Here's an example radargram we can collect with our radar system. Essentially, it is a cross-section view of the ice sheet. You can see the surface of the ice sheet on the top and bedrock reflection on the bottom. So we can measure the thickness of the ice sheet, we can measure the subglacial topography, and we can get this updated basal topography map on the left. So we have a better image of the South Pole Basin. We have a better image of the mountains within the South Pole Basin and also the highland bounding the South Pole Basin and the southern flank of Dome as well. We can also calculate the roughness of the basal topography. So the roughness essentially is the deviation of basal topography over a certain window. It describes how rough or how smooth the basal topography is. This map, I believe we used the window of 400 meters, if I'm not mistaken. So you can see the South Pole Basin is quite smooth, especially comparing to, again, the Gambersiv mountain beneath Dome A, which is known for its rough topography. Another thing we can do with the radargrams, we can trace the internal reflections. So if you work with geologic strata is very similar. Ice is a mineral after all, right? So a very similar principle, we can essentially get a sense of the ice history from this stratigraphy. And we can date those reflections by comparing them to nearby ice cores, if there's an ice core nearby. And those stratigraphy, each individual horizons, they're formed by essentially ice particles that were deposited on the surface of the ice sheet at a certain time in the past. And they will have the same dielectric contrast. They will be compact into ice and will flow with the ice sheet, and they will show up in our radar sounding survey as one continuous horizon within the ice sheet. And we can actually mimic this process in models. So we can build models to simulate this process. We can then simulate the resulting in glacial stratigraphy, which can then be compared to what we see in radar. So that's a deep time component. And in terms of deep structure, we can see the ice, we can see through the ice sheet with our radar, and we can also use potential field data set to look into the subglacial geology, so we can get a sense of the deep structure beneath the ice sheet. So this talk will be focusing on the southern flank of Dome A, where we're trying to find old continuous ice core. And to do that, we need to understand a few components and processes of the coupled ice sheet system here. So going from bottom up, we have the geothermal flux. In some region, we have higher geothermal flux. In some part, we have lower, colder thermal condition. And on top of that, we have a shallow mesosphere structure that could redistribute this background geothermal flux. When conditions are right, we may have basal melting, and water will flow if there's a way for them to flow away, either through the channels between ice and bedrock or through groundwater aquifer, if there is a groundwater aquifer. Of course, we have basal topography and roughness. I talked about them. And we have internal structure, particularly the basal ice, the very bottom portion of the ice sheet. And we have ice flow, and we have surface accumulation. Some part we have higher accumulation, some part we have lower. So there's definitely a spatial pattern to it. But also there's this temporal dimension as well. They change over time across glacial and interglacial cycle. Right? So for the first part of my talk, I will focus on the deep structure, where I'll talk about the state of the basal ice, basal topography, and hydrology and geology. And for the second part, I'll talk about the deep time component. I always want to give the takeaway message up front so that you can keep it in mind while I go through this process of how we came up to this conclusion. Or if you got distracted by your phone middle talk, you won't, totally get lost. So essentially for this part, we believe there is a spatial heterogeneity in the basal thermal condition. And we believe that spatial heterogeneity is caused by subglacial geology. So that's the overall takeaway message. Coming back to this radargram, I talked about the surface of the ice sheet, I talked about basal topography, I talked about internal stratigraphy. One thing I have missed out so far is the basal unit. It's the very bottom portion of the ice sheet where we just don't see those beautiful stratigraphy as we see for the majority of the ice sheet. And we can actually map out the thickness variation of the basal unit. And we see a very interesting spatial pattern in the thickness variation. So we have thicker basal unit in the upstream region, and we have thinner basal unit further downstream. And you can see during this transition, there's a part of the region where this thickness changed very rapidly. You can see the contour being compacted along this line. So we trace this transition out, and we plot this transition on the basal topography map. And we realize there's no obvious correlation between this transition and subglacial topography. So topography is not controlling the basal unit change, something else is. Yes, they do not correlate. During the mapping process, we noticed the basal unit typically shows up in one of two ways. So it either shows up as totally echo-free, so there's no echo power at all other than some noise, or it shows up filled up with those incoherent echoes. So our radar sounder is able to pick up some echo, but they are not in a form that we can trace them or a clear stratigraphy. So we can then map out the presence and variation of this incoherent echo within the basal unit. And you can see the top of the basal unit being marked in white and the bottom of the incoherent echo being marked in yellow. So during this mapping process, we noticed two things. One, the upstream part of the survey region the basal unit is filled with this incoherent echo. It's almost entirely filled with this incoherent echo. And it would disappear gradually as the ice flows downstream. So that's the first thing. And the second thing we notice, when the incoherent echo disappears, it always disappears from bottom first, i.e. the bottom portion of the basal unit would become echo-free first before the whole basal unit become echo-free. So you can see the top part of the basal unit still has some incoherent echo in there, while the bottom portion is already echo-free. So those are three example profiles I showed here, but essentially we see this pattern all across the data set. You can see the upstream region. So this map shows the percentage of the basal unit being filled with incoherent echo. You can see the upstream part is almost 100% incoherent echo, and that percentage decrease as ice falls downstream. Another thing we did is called delayed Doppler analysis. So essentially, it is something we can do to separate out nadar reflection from off-nadar reflection. So what do I mean by that? Our radar sounder can pick up reflections from a range of angles beneath our aircraft. Some of them come back from right beneath our aircraft. Some of them, a little bit off to the side. So we call them nadar versus off-nadar reflection. And delayed Doppler analysis can help us separate nadar reflection from off-nadar. And then what we can do is for each individual reflector, we can see whether it shows up in one specific angular view or does it show up in all angular view. So in this case, on the top here, this specific reflector only shows up in nadar view and does not show up in off-nadar view. That means the energy is bouncing back is at a very well-defined angle. So it's only coming back to us at a very well-defined angle. But if we can see a reflector in all different angular views, it must means that the energy is bouncing back is scattered toward all directions. So that's how we distinguish specular reflector versus scattering reflector. We can then do it for the whole data set for each pixel in the radargram. And here's one of the examples. So blue means overwhelmingly specular and yellow means overwhelmingly scattering. So for the internal stratigraphy, we see they are overwhelmingly specular. Blue color is specular. And for the incoherent echo, it's overwhelmingly scattering. So it is indeed a change of the nature of the reflector. It's hard to tell why exactly that change happened without a core, but we can certainly get some sense from what we can see in radar. So again, we're already at the very upstream end of the survey, but fortunately, our survey is connected to some pre-existing data set. So what we can do is we can compare the radargram at their intersecting point. So we have the COLDEX survey on the left, and we have the A-gap survey on the right. So ice goes from right to left. So in this comparison, you can actually see this continuity of the incoherent echo coming off from the Dome A Gambursiv mountain region into the COLDEX region. So again, Dome A region is known for two things. One is extremely rough subglacial topography. It's all ridges and valleys. And two, it has been shown that there are a lot of basal freezing happening in the Dome A region. So there's water being actively frozen to the bed of the ice sheet. So two things can happen during that process. One, sediment could be entrained to the bottom of the ice sheet during this basal freeze-on process that could serve as scattering reflector or break up the coherency of those specular reflector and make them scattering. And two, you can imagine when ice flows over such a rough terrain and goes from slippery water spots to basal freeze-on packages, the basal coherency of the ice is going to be totally disturbed, and the reflector may turn into specular during this process. And that's what we believe is happening here that gave us those scattering reflectors. Another thing we did is we calculated the vertical gradient of this transition from specular into scattering, and we want to focus on this gradient at the very top of the basal unit. So essentially we see two things. We either have a very sharp transition, very high value gradient at the top of the basal unit, or we have a very gradual decay of the specular energy at the top of the basal unit. So essentially we have two types of basal unit top boundaries. So that's all the observation points I want to present before I show our hypothesis. Oh, sorry. Yeah, we see this not only for that one specific radiogram, we see this for the whole data set. We have a very sharp transition in the upstream region and very gradual decay in the downstream region. So our hypothesis is this. For our region, we have essentially a heterogeneity in the basal thermal condition, with the upstream region being colder and the downstream region being warmer. And it is warm enough that ice is actively melting at the bottom in the downstream region. And the bottom of the ice sheet is filled with scattering reflector. So if our radar can see through the ice column and see everything, this is what we would see. Right, the basal unit gets actively thinner and thinner, with the basal unit all filled with scattering echo. That's assuming our radar can see everything. But the problem is higher temperature would mean higher elevation. Radar wave would attenuate much faster if the ice is warmer. So that's a problem because, the basal reflections are already very weak. So if they go through extreme attenuation, it's very likely they would decay beneath the noise floor of our radar system. So our radar system can no longer separate them from noise. We as human cannot visually distinguish that from the noise floor. So essentially, the top of the basal unit we see in radar is one of two things. The shallower one of two things. It's either where specular reflector is being replaced by scattering, or it's where the basal echoes decayed beneath the detection limit of our radar system. So that's why we think there's a heterogeneity in the basal thermal condition. And this hypothesis is supported by this branch of observation, but also another kind of independent branch of evidence. So this figure is from Megan Kerr, who is a graduate student at UTIG. She published a paper earlier this year, essentially looking into the subglacial hydraulic condition using the same data set. So she calculated the specularity content for the basal reflection, not the basal unit, but the reflection from the ice bed interface. And she also calculated the gradient of the hydraulic potential, and essentially she marked out the areas of the region where subglacial water could be present. And as it turns out, you can see the subglacial basin on this map. You can see Dome A and the highlight here. And as this line in the middle is the basal unit transition line I showed earlier. As it turns out, almost all the subglacial lakes are within the inner South Pole Basin between the basal unit transition line and South Pole, so downstream from the basal unit transition line. So there's a very strong contrast in the in the basal thermal condition in terms of hydrology, but also essentially about the thermal condition as well. What Megan then did is she looked at all the continental scale model of Antarctic geothermal flux, and her conclusion is that none of those models has the spatial pattern that is necessary to produce this contrast in basal thermal condition. So her argument is that we're missing something, and the thing we're missing is subglacial geology. Shallow mesosphere structure is actively redistributing the background geothermal flux. So that's, to me, it's more of a hypothesis than a conclusion. No offense to Megan, but it's a hypothesis waiting to test. There's ongoing work testing this hypothesis. Like I mentioned, Megan is leading the analysis of the potential field data. And on top of the potential field analysis, we do have one additional season of ground-based geophysical survey where we did ground-based radar, we did MT that can look into the groundwater property, and we have passive seismic nodes deployed during the survey. So you can see this is the configuration of the survey array. Oh, yeah, please. So this is Megan deploying one of the nodes. You can't see her face here, but it is Megan. So yeah, it will be very exciting to see what we can find using this new ground-based geophysical data set. Coming back to the conclusion, we believe there is a spatial heterogeneity in the basal thermal condition, with the upstream part being colder and downstream part being warmer. And we believe the reason for that is subglacial geology. So far, so good? Cool. So for the next part of my talk, I want to focus on the deep time component of the system, particularly the ice flow and surface accumulation, how they are now and how they have changed in the past. Again, the takeaway message is we believe for this part of Antarctica, the ice flow has been relatively stable during the past glacial cycle, and we believe our region shows the diversity in terms of the climate evolution across the continent. Again, coming back to this radiogram, we have 9 horizons traced out so far that we kind of know the age of. The shallowest one here is estimated to be around 4.9 thousand years old. It's so shallow that its depth and shape is almost entirely controlled by surface accumulation. We cannot see that for some of the deeper layers, some of the deeper ones here, because they have been in the ice sheet for so long, many other factors may come into play. But for the shallowest one here, we can very confidently say that its shape is overwhelmingly controlled by surface accumulation. So what we can do is we can take the depths of this horizon and we can invert for the average accumulation between now and 4.9 thousand years before present, while ignoring other factors. So this is the result. Our result shows a very low accumulation rate at the upstream part, which is what we want, right? It'll give us probably a higher chance of having old ice at the bottom, and the accumulation rate increased as ice flows downward. We also compared our inversion result with RACMO. So RACMO is this continental model of surface accumulation across Antarctica. Is constrained by observations scattered around the continent. You can see for the most part, at least for the upstream region, our result agrees pretty well with the RACMO model. There's definitely some part where those two results do not agree. That is where we're over a subglacial headland, so there's extreme topographic change in this part, and you can tell the ice is kind of doing a 90-degree turn when it flows, right? It goes like this and turn here. So that's probably why our model breaks in those parts. But at least for the upper stream region, our model passed the test. Or I guess you can argue it is RACMO that is passing the test here, because RACMO is a model and we have the first observation-based estimation of surface accumulation. Anyway, they agree, which is good. We're happy. So that's the contemporary condition. Now we want to think about how it has changed in the past. We want to think about how its pattern has changed and how its rate has changed. So when going through the radiogram, we notice in some part of the region, typically in the upstream part of the region, we had this unconformity going across the internal stratigraphy, cutting through the internal stratigraphy and breaking up the continuity of those horizons. They are results of surface wind scour. So strong surface wind blowing away the snow is deposited on the surface of ice sheet, essentially break up the continuity of the stratigraphy. And we can actually simulate this process. We can simulate the impact of wind scour in our model. What we realize is we can actually reproduce the shape and depth of this unconformity very well by a very simple setup of the model. So the red circle in this panel is what we see in radar, the shape and depth of the unconformity. And the lines here are just some model simulated unconformity shape and depth with a very simple model setup. We kept the ice flow stable and non-changing for the whole duration of time, and we kept the surface accumulation pattern constant. We just put a score zone there, and our model gave us a unconformity that matches with observation pretty well. So that means it is probably what is happening or what has been happening in real world. The real life ice flow and surface accumulation pattern have probably been very stable for the past glacial cycle. There is some mismatch, as you can see. This is the simulated unconformity. It kind of goes off, which means, well, the accumulation pattern has been stable overall. The rate may have changed, right? You can keep the waveform, shape constant and change the amplitude. So that's the overall idea. We kind of expect the accumulation rate to change, right? Because it is controlled by Earth's climate condition, and we know Earth's climate condition has been changing during glacial interglacial cycles. So this panel on the right shows some of the core derived accumulation history at different parts of Antarctica. So you can see it definitely goes through some changes across glacial interglacial cycles. And if you divide each individual curve by their contemporary rate, you will essentially get this percentage change evolution curve with time, how it has changed in comparing to its contemporary rate. So you can see they follow the overall same trend, glacial interglacial cycle, but they do not agree exactly with each other. There's some difference in their exact evolution, which is, to me, not very surprising, because remember, Antarctica is huge. You can fit the continental US onto the Antarctic map and with some room to spare, right? So saying that the whole continent went through the exact same climate evolution is somewhat equivalent of saying, Seattle, Washington and Austin, Texas have the same climate condition, which I can tell you from personal experience, they do not. So it's not surprising, different cores give us slightly different variation, but then the question is, how about our region? How about our part of Antarctica? How the accumulation has changed in the past? Coming back to the diagram, what we can do is we can use those traced internal stratigraphy and use this evolution curve, feed both of them into our model and see how well we can reproduce the internal stratigraphy we see. So this curve is from the Epica Dome sea ice core. That's the one I showed at the very beginning of this talk, one of the oldest continuous record. We can take this percentage change curve, feed it into the model, and we can take the contemporary accumulation forcing, feed it into the model, and see how well the model reproduce the stratigraphy we see. And we can calculate the mismatch. So this figure shows the mismatch for one of the profiles. Surface of the ice sheet on the top, bottom is the bedrock reflection. The traced internal horizons are shown in the middle with their color representing the mismatch between model and observation. Yellowish color is what we want, it's very minimal mismatch. Blue means the modeled layers are not deep enough, and red color means the modeled layers are too deep or deeper than what we see in radar. So you can see if we feed the original dome sea curve into the model, there's definitely some mismatch, especially in the middle portion of the ice sheet. This part, I think the mismatch even maxed out the color bar. It's over 400-meter mismatch, which is not good. It's not what we want. So we started modulating this evolution curve, trying to find the optimal match. So this is the result we got. This kind of band shows the accumulation forcing change that can give us a relatively optimal match. There's still some remnant mismatch because there's only so much mismatch you can get rid of by changing the accumulation forcing only, right? But overall, we got a much better match. And so our model tells us in our part of Antarctica, the southern flank of Dome A, we received higher accumulation than what would be directly inferred from Dome C curve between now and 90 years. 90,000 years before present. So the accumulation forcing is actually closer to contemporary condition during this period of time. So our region probably went through a more moderate climate change than the Dome C region. Beyond that, beyond 90,000 years, around interglacial, our model tells us it's the other way around. We received less accumulation. However, for this particular part, I would take it with a grain of salt because as you can see, there's no additional constraint for the model during this time period. This is 70,000 years of time around interglacial when we expect extreme change to happen, and we simply don't have additional constraints for this part of the model. So you can imagine if we cut this part into two pieces, with one receiving more accumulation, one receiving even less accumulation, the combination of these two can probably give us a very similar result. So for this part, we do not know for sure for this part, but for the younger part, we are pretty confident in the result. And this is one of the profiles we run this experiment on. There are some additional profiles, and the conclusion is quite consistent across those different profiles. And another one. So what we have learned so far, we think the ice flow configuration in this part of Antarctica is relatively stable for the past glacial cycle. And we think our part of Antarctica went through a different climate change than Dome C region, which essentially shows the diversified climate evolution across the continent. I still have some time, so I will give a quick shout out. Oh, sorry, before that. If we were to drill a core in the southern flank of Dome A, particularly outer South Pole Basin, what would we get? We know the base of the ice sheet is probably very cold with no basal melting, which is good, which is what we want. And the ice flow condition has been stable, which is another good sign. And accumulation rate has been low, again, it's a good sign. And having a core here would actually contribute to a more comprehensive ice core archive because it will show a slightly different climate variation in the past. So that's the work I have been involved with. I'll give a quick shout out to the Allen Hills team. Again, we're no longer looking for continuous ice core here. We're looking for some old snapshot cores on the edge of the ice sheet here. So a lot of exciting results have already come out from this work. This figure is from Shackleton et al. That's published last year. You can see from one of the cores COLDEX got in this region, 1902, the oldest age is around 6 million years old, which is quite impressive. And some of the paper already came out, just a few weeks ago, 2 back-to-back Nature paper came out of this work. I'm pretty sure there's more to come in the future. And you can see such 6 million years old ice is being preserved at the depths of around 200 meters, which is very manageable comparing to the interior core, where we're typically talking about, 1,000 meters or even 2,000 meters drilling. So it's very manageable to drill a core here. And the reason why such old ice could be preserved at a shallow depth essentially is because of a combination of extreme basal topography, ice flow condition, and surface mass balance. Old ice is being preserved or essentially stagnant and stuck in some part of the region. So this figure is from a paper that is currently in review led by a graduate student at UW. He ran a numerical simulation of the ice flow condition and showed some parts of the region where old ice can be preserved at a shallow depths. So the COLDEX team has proposed a 5-year renew of the center. If granted, we will go and collect a much more comprehensive, denser, and broader airborne geophysical survey of the Allen Hill region so that we can have a better understanding of what exactly is going on in this part of Antarctica, but for blue ice regions across Antarctica as well. I still have some time. I'll mention some of ongoing work. So this is one of the optimal mismatch plot. You can see there's still some mismatch we cannot get rid of by changing surface accumulation. And there's a special pattern to that, right? Turning from modeled layers being too deep to modeled layers being too shallow. Our hypothesis is this mismatch is caused by some basal porosis that we are not representing well enough in our model. And if you plot the ground geophysical side on this figure, it'll be right here, right downstream of that mismatch pattern. So it'll be very interesting to see or to connect what we can learn from accumulation modeling to what we can learn from the ground geophysical dataset. So it's a handshake of deep time evolution and deep structure. I believe that's all I want to present today, and I'm happy to take any questions.
Questions for Shuai, and I'll run around with a microphone.
Wow, that was really cool. Thank you. I have a lot of questions, but I'll stick with just one right now, which is interpreting or refining the accumulation record based on the interior, based on the englacial stratigraphy. Really exciting. I'm wondering instead of adjusting, so if we just assume that the Dome C record is like truth, and then readjust it, which it's not, I'm with you on that. But what would happen if you readjusted the interpretations of the layer tracking to match the Dome C accumulation? Like perhaps, and I've only traced seismic in undergrad, and sometimes it's really hard to figure out which layer is connected to what if there's some uniformity. What if they're all, should be shifted down by a couple? I don't know. Have you thought about that?
I definitely have thought about that. It's definitely something worth trying, but that would add another item to Shimagani's to-do list, which I don't think she will appreciate. But it's definitely something worth thinking, right? Essentially, to go the other way, the other direction, right? Now we are going from stratigraphy and looking into accumulation, but you're suggesting going from accumulation history we have and using that to support horizon tracing, which is definitely interesting. Yeah, we're just limited by manpower. Yeah.
Fantastic talk. Thank you. Okay, I have one first question on slide 33.
Okay, give me 1 second. There we go.
Okay, so you can fit the position of this stratigraphic unconformity. First of all, fascinating that there's this stratigraphic unconformity that's preserved. You can fit it, and I think what I'm seeing is the way that you fit that is by having the accumulation rate go to 0 during marine isotope stage 11. Is that?
Which figure are you referring to? Which
panel B?
Panel B, yes. Yes.
So I find that super fascinating, and I just wonder if you could speak a little bit towards what the idea of the mechanism is there that would give you a sort of tens of thousands of years just pause in accumulation.
Yes. So, okay.
Maybe that's a wrong interpretation.
No, this is a great question.
Just emphasizing that that's distance along there, so it's not a time. Oh, okay.
Yeah, great. How you get that kind of variation as a function of distance?
Yes, okay. So this is not the first time we see unconformity in radargram, and this is not the first time we know there's wind scour or snow drift on top of ice, right? There's actually a study more than 10 years ago by Das et al. Looking into all the wind scour across Antarctica and predicted extreme wind scour in some part of the survey region. So we knew that there could be wind scour, especially near the upstream part of the survey region. And they actually matches pretty well with our radar observation of the unconformity. So the very top of the unconformity is where it is predicted for there to be wind scour. So essentially wind redistribution of snow deposition by surface wind and surface elevation configuration.
Okay, I see. Thank you so much. It's fascinating. The other question that I had was about this sharp boundary and geothermal heat flux that seems to be like not represented by any of the models. What is just thinking about the timescales over which geothermal heat flux may change, and like recognizing that relatively nearby there are there's active volcanism. Do you think what you're seeing is representing a long-term background signal or like more recent changes? And how do you differentiate between those?
That's a great question. Yeah, I don't think we have thought about the temporal dimension of the geothermal flux, have we? I'm referring to Megan.
No.
But I believe there was this hypothesis of, because we have such a, it's predicted this part of Antarctica. Let me actually show another figure. Point out backup slide. Yes. So it's predicted that we have a thick sediment basin here. So this figure is from Lee et al. They used supervised machine learning to predict the presence of sedimentary basin across Antarctica. It's predicted that we have a thick sedimentary basin here. And I believe there's hypothesis going on, water being actively melted and go into this sedimentary basin and form essentially a groundwater circulation in this region. And I believe that could be temporarily changing, right? Because subglacial hydrology is super sensitive to ice sheet configuration across glacial cycle. So I can definitely see that being one of the temporal changing component of the system. And I believe we had a system floating around of subglacial superflood. Megan brought that up some point in the past. That was a long time ago, but it's one of the hypotheses, right? There could be a superflood event happen in the past. So yeah.
Okay. In Duncan's paper, he talks about a possible subglacial deposition of sediment as the basal layer melts and the sediments get deposited as it melts. And that's obvious. The temporal element.
That's a great question. Thank you. Yes.
So you showed the mismatch between the horizons and the model horizons, right?
Yeah.
And then you're comparing it to the climate forcing derived from cores and sort of constructing a spread of how much the accumulation can vary. How do you deconvolve the contribution from the climatic variations and the uncertainties from the temporal controls on the isochrones?
So what's the last part of the question? The temporal control of?
So how do you deconvolve the climatic variations from the temporal controls we have on the isochrones from the ice core?
Oh, yeah. Yes. So uncertainty, essentially. Great question, because one, our radar is not perfect. There's this limit of resolution, and tracing the horizons in some part of the region is not easy. There could be some human cost uncertainty involved in that tracing process, and core is not great. So that's why I'm showing a band of accumulation forcing instead of just one single value. And also our model is not perfect. It's a 2.5 dimensional model, so not full 3D. And for the most part, we use shallow ice approximation, which is a very low order physics representing the ice dynamics here. So there's a sensitivity element going into the mismatch evaluation as well. So essentially what we found is for a range of accumulation forcing, any accumulation forcing within this range can give us a mismatch that is smaller than one, the age uncertainty of the horizons, and two, essentially the sensitivity value of the model. So that's where our limit is. We cannot discriminate against any accumulation forcing within this band. So we have to accept it. But the good thing is they do show a kind of a, kind of a consistent conclusion.
So is the spread or the result you can get from this spread of accumulation way smaller than the uncertainty induced variations in the modeled isochrones?
Yes, yes. Well, I guess it's a shout out to you. You did a pretty good job tracing the horizons. The uncertainty involved in that is actually much smaller than the model we're using here. The other way of saying our model is not good enough to match your tracing quantity. If that's, but I will say there will be more analysis going into this, especially, I talked about trying to figure out what is going on here, giving us this remnant mismatch will probably involve a higher order physics model, probably a full Stokes even, a higher grid resolution as well. And there's APRS, which again requires much higher spatial resolution and temporal resolution as well. So all I'm saying is your work didn't go into waste. Your work of really constraining the details of the uncertainty of the age and depths will be useful for future study. Does that?
Thanks.
I have a question about the delayed Doppler processing.
Yes.
So when you're looking at the basal unit specularity, you're just tracing like where is the reflector in terms of if it's nadir or off nadir.
Mhm.
I was curious if you saw any like relative, like how the relative difference between like the power reflection differed when you're closer to that basal unit between the nadir and off nadir versus higher up in the ice column.
That's a great question. I did try to look into that component. I believe using Landmark, I got this average echo strength of that incoherent or the fuzzy cloud in there. But the problem is it's kind of a circular logic because we don't know the exact attenuation rate. So we can't do an accurate attenuation compensation to give us the true echo strength of that fuzzy cloud. Do you know what I'm talking about?
Yeah, I mean, I just like relative, like just the nadir to off nadir, like obviously within the same, I guess, isochrone, like you wouldn't have to worry about attenuation rate varying that much, but like just kind of that ratio of like, because a portion of that might play into like how specular something is if the difference isn't, that much.
Yeah, in that sense, I couldn't recall. I couldn't recall seeing a very obvious contrast as we see in radar. But again, that's before we do any attenuation compensation. So I don't know whether that answers your question or not.
Sorry.
It's okay. So from what I can remember, tracing those echoes and looking at the delayed Doppler, I don't remember seeing a strong contrast in terms of the echo strengths. But again, that's before attenuation compensation.
I'm just thinking like if you're looking within one, I guess, not trace, I guess isochrone line.
Oh,
Those should have relatively similar rates of attenuation, and comparing the power return from nadir versus off nadir might give you some more information about specularity and heat flux.
I think I see what you're asking. So this figure actually shows the power ratio between specular and scattering reflector.
I mean, like within the, like you have your Doppler frequency, you have the nadir, which is center, and then you have off nadir, and you're basically saying if the reflector shows up in all three, it's a scattering body. And I'm just thinking, would the power difference of that same reflector from off nadir to nadir give you any more information?
Oh, yes. I see where that comes from. Yes, something like that would be very useful to do for basal reflection.
Yeah.
The reflection from the ice bed interface, because we expect a lot of changes in terms of the material at that interface. I do not think we're expecting such dramatic change of material in glacially.
Yeah, no, I was mostly thinking about the basal unit
Yeah,
itself.
definitely, yes.
See the most of like I guess, the scattering behavior and how like that potentially
yep.
would contribute.
That can definitely go, it goes into the geologic model. It can give us another point of reference when we build our geologic model to fit the potential field dataset. But that's only the very shallow part of the lithosphere. Our radar cannot see through the bedrock, so that'll give you a sense of the very shallow portion of the lithosphere. So, but yeah, that's definitely something available to do.
Other questions?
This to a glaciologist may be a incredibly stupid question, but I'm a geologist. When you interpret that feature as an unconformity, if that was a sequence of water lane or aeolian sediments, you would be crossing lines of diachronous lines rather than interpreting. It would be a series of different events rather than through the sequence of sediments, as the ice is, rather than an unconformity. It would be a series of perhaps dune-like features, for instance, if it was aeolian or shallow water marine driven by wind. So I don't quite understand how you justify correlating across the strata, so to speak, as an unconformity.
Yes, that's a good point. So let me go back to that figure. Give me 1 second. Or here. I guess the question is about the age depth scale across the unconformity, on the two sides of the unconformity, right?
Yeah, in other words, at the tips of the arrow, you're interpreting that as one surface, right?
Yes.
As an unconformity. Why not a series of of similar events stacked up through time?
Stacked up.
Stacked up through time. The same process going on, but through time.
Same event going on. I'm kind of.
No, but you're interpreting that as one surface.
Yes. Oh, you mean it could be created by multiple different events that so the mechanism kind of turns on and off through time. It could be, but we would expect the unconformity to be not continuous in that case, right? There will be a breakup in the unconformity. Would that be the case?
Yeah, I guess I see breaks in
it. Yeah, you can argue there is probably a break here, right? You can see the layer being continued. Yeah, I guess it could be true. We can definitely try that for using our model. It should be fairly easy to try. Yeah.
Thank you. Interesting talk.
Thanks. That's a great question.
Any other questions? Okay. So with that, thanks everyone. So Shivangani will be organizing lunch, and they'll continue the discussion, I'm sure. Actually, we're hosting the COLDEX annual meeting in the middle of summer, first week of August. I've sent around an invite. So if people are interested here in signing up, just get in contact with me. You're larger range of ice core in science. And then lastly, Shuai does have additional sign-up slots this afternoon available if you wish to speak to him. So with that, thanks Shuai again.